Welcome. In this seminar, we're going to talk about oxygen concentrators. We'll talk a little bit about concentrators in general. What are they? What do they do? Ask and answer the question, why might we use one? Talk about what's the difference between concentrator oxygen versus what we might consider more standard oxygen, for instance from a cylinder or a typical wall outlet. What the applications and types of different concentrators available are. Naturally, we need to consider in today's environment a little bit about what concentrators do or don't do in terms of helping us deal with COVID. And we want to talk a little bit about the use and safety with concentrators. It's important that you ask any questions that you have. At the end of the session, we'll give you an email address that you can send those in, and we'll try and answer them as much as we possibly can. It's important that you understand and are able to make informed decisions for your facility and your patients. Okay, oxygen, we pretty much know what that's all about. We have to have it to survive, we have to have it to breathe, so we're going to put it through ventilators. We're going to administer it to patients through nasal cannula and masks. That's typical of the pre-COVID, but also now with COVID we do it even more so, but in different ways. You can use it for resuscitation through things like an ambu bag or breathing bag. Of course, we traditionally have used it for treatment for chronic obstructive pulmonary disease, carbon monoxide and carbon dioxide poisoning. We would use oxygen at high flows for those purposes. And we would use nebulizers, turn the drugs into a mist, if you will, and then breathe those in. So oxygen was used as a way to convey drugs. All oxygen comes in the same place, and that is, we take it from standard air. Standard air consists of 20.9% oxygen, 78% nitrogen, and about 1% of other things, most of which is argon. Then, of course, you have carbon dioxide and krypton and helium and hydrogen, all these different gases in tiny quantities. So traditionally, if we wanted to supply a hospital with oxygen, we were going to do it in liquid form, in what's called a container, or in gaseous form, in what we term a cylinder. We're familiar with both of these things. The big white tank outside our hospital is a container, and of course cylinders we see every day and throughout the hospital. Liquid is the real way this is done, of course, because if we buy oxygen, it's almost certainly produced by liquefaction. And that means we're going to take air, we're going to liquefy the air, we're going to break that liquid into various constituent gases, oxygen, nitrogen, argon, in liquid form. We do all that at an air separation plant. Now we have liquid oxygen, that's very nice, but we have to make it useful, which means we have to put it on a truck, haul it to our facility, fill that big white tank, and that's how we will get liquid oxygen and use it in our facility. But if we want cylinders, we're going to take it from the same source. Air separation plant is still going to make it in liquid form. They're going to take that liquid oxygen, they're going to turn it into a gas, compress it at high pressure into a cylinder, 155 bar, about 2200 psi. We're going to put that cylinder on a truck and we're going to take it to the facility. So in all cases, we're going to make it in much the same way. We're going to have to transport it to site. And that's where the tyranny of distance comes in. Transportation is the biggest challenge in all oxygen supply questions. With liquid, we can only store it so long, we can only transport it so far because it's a use it or lose it situation. Liquid oxygen will gradually boil off, and we're going to lose some oxygen as we transport it. In both cases of liquid and cylinders, they're very heavy, very challenging to transport. And with cylinders, the pressure is very high, 2200 psi typically. They have to be handled with appropriate care. And that's one of the things about having oxygen delivered is we do have that burden of handling. A cylinder doesn't contain a great deal of gas, about 240 cubic feet, 6,900 liters. So if you have a very large facility using a lot of oxygen, it's just too much handling to deal with all those cylinders. They cost money to rent. Every month you usually get charged for the rental of the cylinder itself. And if by chance you lose that cylinder or it gets stolen, you're still responsible for paying for it. So when would it make sense to produce your own oxygen? Well, obviously the first case is where you're likely to have a supply interruption, seismic activity, tsunamis, volcanic activity, severe weather, storms, snow storms, typhoons, hurricanes. If you had or lived in an area which was unstable, civil unrest, where you had industrial action, where there might be a chance that the transportation would not be possible or the air separation plant would be closed by industrial action. And of course, if you have transportation questions, a good example of this is the hospitals in Alaska. Many of them have concentrators because the only way to get oxygen to Alaska is to bring it by ship up the inner passage, and well, you can have that ship sink. So if that ship sank, there would be no oxygen in these hospitals. Making it for themselves makes sense. Obviously, if you couldn't get oxygen, a good example might be a place like Bermuda. How would you get oxygen to a place like Bermuda? Well, you'd have to put it on a ship, probably in Miami, transport it over. Big hassle. Makes more sense to produce it yourself on site. So any remote area or islands, an undeveloped area, not too big a problem in the continental United States, although some Indian reservations, for instance, do have difficulties with transportation, and concentrators are considered in such places. One of the more interesting ones is what's called the urban island. And the urban island is all about the situation where the hospital's built up the site that it occupies to the point where it doesn't have anywhere that the truck could go park while it was filling the big white tank, or in fact no place for the big white tank to go which is safe. So now what do? How do we deal with that oxygen need? Maybe the land that we want to put the big white tank on is in fact so valuable and we'd rather put a 10-story patient tower on it. What then? Well, there's another case where we might want to think about, rather than having oxygen delivered, we would actually have it produced on site. And of course, nowadays we're very aware of this one, but we've been for a while because these mobile hospitals, the Mississippi Med is shown here, there's one here in the Carolinas, they're all over the country they have these, and they are all about emergency preparedness, a hurricane, tornado, etc. And now with the COVID, we have to concern ourselves with, do we have enough oxygen? Is it a good idea to have concentrator in the facility in order to supplement our supply? All concentrators work in much the same way. You use a molecular sieve material. It's called zeolite. It has pores in the molecular structure, which are about the right size to capture the various gas molecules. Now, it doesn't hold them permanently. It just slows them up. So as they pass through the packing or through the column where the zeolite is packed, we're going to go ahead and relatively slow down one gas relative to another. So the zeolite is going to absorb or hold back one gas and allow the other to pass more quickly. And by doing this, we can draw off a very high purity concentration of oxygen or of nitrogen. And the interesting thing about the concentrator as we have it, it actually is a very good argon concentrator. It's probably a better argon concentrator than it is an oxygen concentrator, which means that the oxygen that we get out of a concentrator is not 100% pure. It will contain a small fraction of argon and nitrogen. So we don't get from a concentrator oxygen 99% like we would from an oxygen air separation plant. We would get oxygen 93, which is a concentration of 90% oxygen to 96% oxygen, with the balanced gas being primarily argon. Now this is recognized. We have two monographs in the pharmacopoeia for oxygen. One is oxygen and is produced by an air separation plant, has a concentration of 99%, and the other is oxygen 93, produced by a concentrator using a molecular sieve and has a concentration of 90 to 96%. So this is what it looks like. Essentially, two different monographs in the pharmacopoeia, both usable as breathed oxygen, but they have different specifications because of the different way they are produced. Now, this question of argon, is that a problem? Well, the fact of the matter is that no, it's not. In these kind of concentrations, it's been conclusively demonstrated this is not an issue. At 5% concentration, argon is entirely non-toxic. So, for the most part, this is not a problem at all. So, concentrators come in different forms, different sizes, and for different purposes. Probably the one most of us would be familiar with would be the Homecare style concentrator. They're intended for a single patient. They'll produce typically less than 10 liters a minute at a low pressure. So they're not intended like a pipeline to have a high pressure. They're intended to run one nasal cannula, one mask, basically single patient use. They will either be the domiciliary style, which you would use in your house and plug into the wall, or there are now walkers which run off a battery for a limited period of time and allow the patient a certain amount of mobility. Up from there, we have deployable concentrators, which are medium-sized, typically around 20 liters per minute at max, with a pressure output of about 50 psi or less. They are intended primarily to run one or two ventilators in a case where there's no central source. You might see this kind of thing in a military MASH unit, something like that. They also would plug into the wall. They would draw from the wall power. For small clinics, there are medium-sized units. They will be typically up to about 80 liters a minute, although they can be all kinds of different sizes. They will put pressure out about 60 psi, and they are commonly used in small clinics. So you might see them in a surgery center. Veterinary hospitals like these a lot. You see quite a few of them in veterinary use. And you might see them in a freestanding outpatient clinic, which uses relatively little oxygen. And up from there, we have the full hospital systems. These are designed to produce oxygen for use in an entire pipeline. They are multiple sourced, and they comply with one of the medical gas standards. Usually in the United States, it would be the NFPA 99. In Canada, the CSA Z 7396-1 or the ISO 7396-1. Several components go into these. You'll start off with a compressor. The air will then pass through a dryer, filters, and activated carbon to make sure any hydrocarbons are removed. Then stored in an air receiver, flows into the concentrator itself, and the concentrator is what's going to extract the nitrogen and concentrate the oxygen. That resulting gas will go into an oxygen receiver through an oxygen filter and into the system. And this is often referred to as the oxygen train, and you can see why. Basically, one component follows another, and the ultimate output is oxygen 93. There is another technology in use called the VSA. This is a version of VSA. There are several around, but this is one of them. And essentially VSA operates at low pressure, so it needs a booster compressor. So the oxygen is going to be produced at a low pressure. It's then going to be boosted to pipeline pressure, 4 to 5 bar, 50, 55 psi through the booster compressor. Oxygen receiver to store the oxygen, a purge recovery tank, which has to do with the internal operation of the concentrator, the molecular sieve itself, the blower module, which produces the gas or the compressed air, I should say, and vacuum for the operation of the molecular sieve. Heat exchanger, a blower and vacuum reversible unit, which is producing both the vacuum and the pressure side on this, and of course intake filtration. So this is an oxygen train in the same sense as you saw the previous one. One is a PSA, pressure swing absorption. This is a VSA, vacuum swing absorption. Both technologies are in common use. So when we talk about medical gas, we have to keep in mind there is always a first rule, and the first rule is that the patient is first. We always want to supply the patient. We want to make sure they have the quality of gas they need, the quantity of gas they need, and that they have that gas continuously. So when we put together a central supply system down in the basement or up in the mechanical room, we want to think about making sure we comply with that first rule. That oxygen train we talked about is going to draw in air, send nitrogen to the vent, and put out oxygen. If anything happens to this oxygen train, we have a power failure, we have a mechanical failure, we would not be able to comply with the first rule. We would not be able to supply the patient. That's not acceptable. So what we want to make sure we can do is always supply the patient. We're going to do that by having at least 2 sources. Now under different codes we have different kinds of sourcing. We have different numbers of sources depending on what the code requires. But generally what we're talking about is an arrangement something like this. We're going to have at least 2 oxygen trains, whether they be PSA or VSA style. And they are going to work to make sure that we're always supplying the patient. Should either of those fail, and of course they're power driven, so if we had an electrical failure, that would be the most common problem we might expect to see. We want to have cylinders to make sure we can supply the patient even in that case. And then all of this is going to be tied together by a variety of equipment to make sure that the supply of gas is maintained. And then the idea is to build this all so that it operates in what's called a cascade. We want to run our 2 oxygen sources so that they alternate. We have the wear equalized. We make sure that they're both continuously operational. If the primary source can't manage the load for any reason, whether we're overdrawing it, whether we have power failure or mechanical failure, any reason that we could not manage the load from the primary source, we want to drop to the secondary source, and we want to have an alarm that tells us that's occurred. It could be a secondary in use alarm, it could be a change of source alarm, different names are given to it, but the idea is we're going to automatically switch from the primary to the secondary, and we're going to get an alarm that tells us that's happened. If for any reason the primary and the secondary cannot manage the load, again, the most common problem you might expect to see would be a power issue. In that case, we want to drop onto those cylinders, draw from those cylinders, and get an alarm that says the reserve is in use. And finally, we want to make sure we have enough gas in the reserve, so we want to have an alarm that tells us when the reserve contents are low. And that would be a reserve low alarm. So it's a little more complicated than this if we go through the code in detail, but this is the basics. We want to have a cascade, we want to drop from primary to the secondary to the reserve, and we want to have an alarm that tells us each time that occurs. Now, if we look at this, we've got two oxygen 93 sources in the form of oxygen trains, and then we have a cylinder source. Well, if I go buy those cylinders from a traditional gas supplier who's using an air liquefaction process, those cylinders are going to contain oxygen 99. The concentrators are going to pack oxygen 93, which of course has a concentration of 90 to 96%, and the cylinders will have a concentration of 99%. Because of the way the cascade works, we could actually end up with a gas that doesn't exist. It's not oxygen 99%. It's not oxygen 90 to 95% on 90 to 96%. It's something else, anywhere between 90 and 99%. Well, this gets a little tricky because the monographs in the pharmacopoeias talk only about the gas between 90 and 95. Now, keep in mind, we're talking about the same gas, we're talking about the same therapeutic benefit and the same therapeutic application. It's just there is this legal question about what is that gas that's between those two numbers. Now, keep in mind that pure oxygen is actually toxic. If we breathe pure oxygen for too long, it can result in hyperoxia. Now, we're not used to hearing that these days. We're used to hearing about hypoxic, basically not having enough oxygen. Here's a case where we have too much. And this can result in permanent blindness, retinopathy, particularly with small infants. It can result in central nervous system toxicity, and it can result in oxidative damage to cell membranes. This is all bad stuff, obviously. That's why we don't want to administer pure oxygen. We always want to mix oxygen with air. Pure oxygen is normally not administered in any clinical therapy. The only time you would typically see pure oxygen used is in resuscitation. Now, normal clinical practice would say we would administer something between 30 and 40% oxygen, fractional inspired oxygen, which means we're taking the oxygen, we're blending it with air to get that kind of a concentration level. Then we would use pulse oximetry to make sure that we were getting the right oxygen saturation in the patient's blood, and we would titrate the oxygen up or down depending on the reaction we got from the patient. So we want to really make sure the patient is getting good saturation. We really don't care so much about the FiO2. However, obviously the two are related. Now, one of the most unusual things about the COVID treatment is that we're seeing very high FiO2s used. So while 30 to 40% is fairly typical for other conditions, we're seeing 50 to 60% in COVID patients. So it's important to recognize that we are going to use more oxygen, and we're going to use it in a somewhat different way with COVID patients than we have been used to with traditional therapies. Now, that doesn't mean that we can't achieve this with concentrator oxygen. Of course we can. We have oxygen 93, 90 to 96% oxygen. We can quite easily attain a FiO2 in the 60% range. Now, what we're seeing is the kind of devices here where we're talking about also very high flow rates. So our traditional therapies that we would do with oxygen might go up to the 15 liters range. With COVID patients, we're seeing some applications up to the 120 liters range. Now, all of that's not oxygen. All of that is oxygen and air, but it's still very high quantities of gas, much higher than we're used to seeing. And that's one of the concerns that we have as we look at our medical gas systems in light of the COVID crisis. Now, oxygen 93 always should be administered with oximetry. Of course, this is really not anything new. Even oxygen 99 should always be administered with oximetry because we're really after saturation in the blood. We are not interested so much in the FiO2 directly. Be aware that you're going to use slightly more oxygen from a concentrator than you would oxygen 99. The difference is very small. Obviously, the difference between 93 and 99% is only 6%. So we're talking about very small changes, but they are significant. So when we're doing our titration, we would see slightly higher use of oxygen with a concentrator. If we're using a concentrator, we have to pay attention to the specifications we're using to purchase our clinical equipment. Ventilators and anesthesia equipment are particularly important here because we need to make sure that they are also usable with the concentrator system. And the reason that this is a concern is there are some devices on the market which use the wall gas for calibration. Now we can argue whether that was ever a good idea, but with a concentrator it's definitely not a good idea because of course the concentrator, the concentration of oxygen from a concentrator can vary somewhat, and if we are assuming 99% from the source gas, we're obviously going to throw off the machine. So it's very important we be aware of that and that the instrumentation and medical equipment that we use is suitable for use with a concentrator, or that we are calibrating it with a reference cylinder. In the case of COVID, obviously the primary symptom of COVID is inability to catch one's breath, a cessation of drowning, in some cases dyspnea, low SpO2. That's the most important finding, is we're finding low saturation of oxygen in the blood. Sometimes it's accompanied by labored breathing, sometimes not. But what it comes down to is many or most COVID patients will need supplemental oxygen. Now the problem that we're finding is the amount of oxygen that they need is very unprecedented. So whereas traditionally we might use 8 liters a minute through a mask or a nasal cannula, that would be a fairly high level, and that would be the total gas. Remember that the FiO2 is then 30%, which means the oxygen is only 0.9 liters a minute. The rest is made up with medical air. We're going to mix oxygen and air to get that FiO2 and deliver the total amount of gas to the patient. Now the reservoir masks, Venturi masks, these take a little more. They will typically take up to 15 liters a minute of gas, 30 to 50% FiO2, 50% being relatively high. Oxygen consumption then is going to be somewhere between 2 and 6 liters a minute. The rest is going to be air. But now we start to get into things where we're treating COVID patients and we start to see standard invasive ventilation. Quantity of gas is not that great, but the FiO2 is very high. So we're starting to consume a fair amount of oxygen this way, 4.4 liters, the remainder made up with medical air. And in this case, of course, the medical air has to be from the wall. We need pressurized medical air. With reservoir masks, Venturi masks, and standard nasal cannula, we can often do that with a Venturi, where we're going to simply feed the patient oxygen and the air component is going to be drawn in through a Venturi. We don't actually ever connect them to the medical air at all. Then we get into some more exotic treatments, which are very common with the COVID patients, and we're seeing 50 liters a minute through high flow nasal cannulas. And we're seeing that with a very high oxygen FiO2, 60%. So we're starting to see very high consumption of oxygen here, 24, 25 liters a minute of oxygen being used into that high flow nasal cannula apparatus. High frequency oscillating ventilators, these will also use very high flow rates, 80 liters a minute, 50% FiO2s, and you can see 50 liters a minute. So we're really getting to where we're drawing quite a lot of oxygen. The findings from COVID are that oxygen demand dramatically increases. In Italy, they had increases as much as 3,000%. Standard supply chains may struggle to keep up with that demand. Concentrators, therefore, have been discussed as solutions or supplements for other supplies. This is quite possible, but we do need to keep in mind we don't want to take a concentrator and plug it into an existing pipeline. For instance, one of those portable concentrators could produce 50 psi oxygen. We could plug that into the wall and try and supplement the amount of oxygen that we have in our pipeline. Not a good idea. And the reason it's not a good idea is because of that 90 to 96 problem. We'll mix those two oxygens and we won't necessarily know what level of oxygen we are providing to our patients. Now, again, it's the same oxygen, it has the same therapeutic benefit, so could it be done? Absolutely. Would it work? Yes, it would, as long as everybody knew what was going on and was using oximetry correctly. Now, it is possible to replace the existing source, change over from liquid to concentrated oxygen for the whole building. Absolutely possible, but it's not a quick process. It requires specialist assistance, specialist equipment, specialist engineering. So in the crisis mode, we're probably not going to do that. However, it is a consideration for the future. Homecare concentrators, those small portable concentrators, should not be used for any but the lowest acuity patients. They cannot produce large amounts of oxygen, they can't produce any pressure, and they can't run a ventilator. So for the most part, those small home care concentrators are useful for masks or nasal cannulas, but not for ventilators or high flow equipment of any kind. One thing to keep in mind about concentrators is that their rating is their rating. You can't get any extra out of them. They don't have stretch capacity. So if we say we've got a concentrator designed for 20 liters a minute, we will not be able to get 25 liters a minute out of it because the concentration will fall. So essentially we'll go from having a 90 to 93% to where we might have 80, 85% concentration or lower. Ultimately, if we draw enough through a concentrator, we'll have no oxygen at all, we'll simply have air. So we really need to make sure that we are aware concentrators have fixed outputs. Can a concentrator be used to refill cylinders? Well, yes, it can. With the right equipment, with the right training, and with appropriate limitations, it is possible, but it's not a casual activity, and it shouldn't be undertaken easily, because cylinder filling can be very dangerous. If you fill a cylinder too fast, the cylinders can explode. If you fill them too often and you don't pay attention to the test dates, they can explode. So filling cylinders on site can be done. It can be done safely, but it needs to be done with appropriate safeties in place. Now, could you go ahead and take those cylinders and sell them and become a gas company? Well, certainly not in the United States. It is almost never appropriate to do this. In most places, it is illegal to do this without the appropriate license. So the answer is no. If you're going to fill cylinders, they are for use on your premises. Ideally, they are for use in fixed locations, so you would fill the cylinder bank that you remember seeing from the earlier diagrams, but you wouldn't want to take those cylinders and distribute them around the hospital. If you did, there are a bunch of considerations about labeling, making sure you control the cylinders, that the cylinders that come from outside and the cylinders that you use within your hospital are kept separated. We want to make sure that our cylinders don't get out into the great wide world and that we don't fill cylinders that don't belong to us. So Difficult thing to do. If we're going to fill cylinders on site, it should be for a fixed purpose, not for moving those cylinders around the building. And we could never take those cylinders and sell them to someone else. Simplified reuse rules for oxygen. And this is very simplified, but good thing to keep in mind. If it can burn, don't let it near. If it can ignite a fire, don't let it near. If you can crash it, don't let it near. We want to make sure that our oxygen concentrator, our manifolds, or our liquid oxygen is secured, that it has gates and locks, and that we make sure that casual passerby can't get at it. We want to make sure we think about the location for the intake. If we're running a concentrator, yes, it will remove all the nasties, the negative gases, the toxic gases that are present in ambient air, but we don't want to challenge it more than it needs to be, because of course all that stuff can damage the zeolite. So we want to make sure we get the best available clean outdoor air. Remember that oxygen from a concentrator is just as dry as oxygen from any other source. We want to make sure we rehumidify it for comfort in breathing. Remember that if we're using a concentrator, a portable concentrator in a patient space, just like any other piece of electrical equipment, if we trip over the plug, it's going to stop the concentrator. So we want to make sure we're paying attention to that. Make sure that temperature is considered. Concentrators do lose capacity as temperature goes up. So the cooler you can keep your concentrator, the more effective it will be, the more oxygen it will put out at a higher concentration. All concentrators need maintenance. The more you run it, the more maintenance you're going to need. That's pretty logical. But keep in mind that even if you don't run them, they may still need maintenance. Small units, portable units, are often maintainable by the biomedical technologists. Larger units will need to be maintained by engineering. The appropriate training is very important, because maintenance is essential. If you don't do your maintenance, you will not be happy with the output from your oxygen concentrator. So the technology is well understood. It works effectively. It does require that you give it appropriate attention. You can't run a concentrator and expect that you can just ignore it. You've got to pay attention to it. You've got to make sure that you understand how the machine works, you have the parts available, and that you perform maintenance as required and on schedule. But given that, concentrator is a very viable way to produce clinically effective oxygen. In some places, it may be the only way. You may have to make some small adjustments to your clinical practice, but they are very small. And if you're following normal practice guidelines with oximetry, those adjustments will be essentially automatic. The question of whether concentrator oxygen is cost effective is a difficult one to answer, because it varies so much with the transportation, the cost of your oxygen, cost of your electricity. It's hard to say if you'll actually get payback from a concentrator. Obviously that can be evaluated, but for the most part it's best not to assume that you will get payback. It needs to be validated. But sometimes other considerations are just more important, and this may be one of those times where that's true. Any questions you have would be welcome. Please use the email address shown, and if you send in a question, we will try hard to get back to you as quickly as we can with an appropriate answer. And we thank you very much for your attention.